Hello, everyone. In this module, we will dig into virtual memory. Throughout this module, we will explore background knowledge, demand paging, page replacement, and thrashing. Now let's start from the background knowledge. Traditionally, we've under the assumption that entire processes must reside in the main memory for execution. So that means the entire logical address space of a process should be placed into the main memory so that this process can run on CPU. But the reality is often different from this ideal. In fact, the entire program or the entire process is not needed during the execution, or only partial logical address space needs to be loaded in the memory during execution. For example, programs often have code to handle unusual error conditions. Since these errors, they don't occur very often, some error handling code may not be used during the execution, or they may never be used during the execution. When we program, we use large data structures. For example, arrays are often allocated more memory than they actually need. So even in some cases, the entire program is needed, but it may not all be needed at the same time. So based on this reality, we may consider the ability to execute partially loaded process in memory. Here are some possible benefits for this ability. 3 benefits. First is program is no longer constrained by the limits of physical memory size. As a programmer, or when a programmer writes a program, they can write a program for a large virtual address space, or write a program for large logical address space. So there's no need to consider the physical memory size. It makes the programming easier. The second benefit is each process takes less memory space while running. So that means more processes can be loaded in the memory at the same time. So we can have higher degree of multi-programming. More processes can be loaded in the memory. Now the higher multi-programming degree, that means we can maximize CPU utilization. The third benefit is less input-output operations would be needed to load or swap processes from the secondary storage into main memory. So each user process would run faster. So we can see running a program that is not entirely in the memory would benefit computer systems and users. This is the motivation of virtual memory. Why do we need the virtual memory? Virtual memory involves the separation of process logical memory or the virtual memory from the physical memory. So that means only part of process logical or the virtual address space needs to be loaded in the physical memory for execution. We don't have to load the entire process or the entire process address space in the main memory for execution. So now a large virtual memory can be provided to programmers. And the programmers can program for a very large virtual memory, even though only a smaller physical memory is available. The physical memory size cannot limit or constrain the virtual memory space. So here again, the benefits of the virtual memory, 3 very important benefits. One is a logical address space or the virtual address space can be much larger than the available physical memory, which makes the programming easier. And more processes can be loaded in the memory and run concurrently or the simultaneously if we have multiple CPU or the CPU cores. And less input-output operations are needed to load or swap processes from the secondary storage to main memory. Each user process can run faster. 3 benefits of virtual memory. This is an example of the virtual memory larger than physical memory. On the left side this is a virtual memory space or the logical memory space for a process. We have the multiple pages here. Now this is a physical memory space or the main memory. Now we can see the main memory is smaller than the virtual memory space. This is a page table. This page table shows which page is loaded in the which frame. The physical memory is divided into frames. The pages are loaded in these frames. So we have the page table to show this mapping. Now some pages are in the backing store and some pages are loaded in the physical memory. A process can run on the CPU with the some pages loaded in the memory. It don't have to be the entire processes loaded in the memory and then the process can run on the CPU. The virtual memory space. Virtual memory space of a process refers to the logical or the virtual view of how process is stored in the memory. Normally, this virtual memory space starts from the minimum address 0. Start at the address 0. This is a minimum virtual address. It exists in contiguous address until the end of space. This is a maximum virtual address. This virtual memory space contains the code section or the text section, data section, heap, and the stack. So here the code section, data section start from the minimum address 0, but the stack section start from the maximum logical address or the maximum virtual address. So when the process running on the CPU, the process called the function, all the function calls information are stored in the stack. For example, the return address of the function, the parameter values, and the local variables are all stored in the stack. So when the process call more and more functions, the stack grows. When the stack grows, the address decreases because the stack starts from the maximum address. And also in the program, if we use the dynamic memory allocation, this dynamic array will be stored in the heap. So we use more dynamic allocation, the heap grows. The heap grows towards stack. So when a heap grows, the address increases. And when the stack grows, the address decreases. So we say the stack grows towards heap. And the heap grows towards stack. And between the heap and the stack, this is the big hole. The blank space, this is the big hole. Unused address space between stack and heap is a hole. It's a large blank space between stack and heap. no physical memory is allocated until the heap or stack grows to a given new page. So the last module, we talked about the paging, non-contiguous memory allocation. So here we use a paging memory allocation method. The physical memory is divided into frames, and the frames allocated or the frames assigned to a process may not be contiguous. We also have the memory management unit maps the logical page to physical frames and translate the logical address or the virtual address to physical addresses. The first video will stop here.